Okay, welcome to the penultimate lecture on evolutionary robotics. Before we talk about soft robots and differentiable robots, let's talk a little bit about the final project. As promised, I'm going to take a few minutes now and talk about the written report and oral presentation. These are two documents that you're going to be submitting by 11:59 p.m. this Monday night. And then the following morning, bright and early in here, you're going to be presenting your oral presentations, all 59 of them. Okay, so we'll talk about how that works. You can see there's a link. There's a link to the written report and oral presentation embedded here in the schedule. When I get back to my office after class, I'll create two new Brightspace assignments where you can submit your written report and your oral presentation. Okay. Not surprisingly, your written report and oral presentation are going to be a summary of your final project and with a specific focus on your A/B testing. Let's talk about the written report first. Worth 7% of your final grade, due Monday night. Please remember to submit it to Brightspace. It must be a PDF, no docx, no txt. If I can't open it, I can't grade it. Okay. Minimum length, 4 pages, double space, 12-point font. If you want to write War and Peace, knock yourself out. But at minimum, in years past, 4 pages should be sufficient to summarize the work that you've been doing for your final project. Okay, so what are you doing at the moment? You're currently performing A/B testing, and you're trying as best you can with whatever devices you have available to collect as many independent evolutionary runs of A, as many independent evolutionary runs of variant B as you can. And then in your written report and oral presentation, you're going to try and prove to us which of these two variants facilitated the evolution of adaptive behavior. It's a fancy way of saying which of the two versions of your code made it easier for the evolutionary algorithm to find highly fit individuals. Lots of different ways you can do this. We talked about fitness curves last time. What we're looking for in this proof is that which variant produced better robots, or whether there is clearly no difference between A and B. If you don't collect enough data, you won't be able to come to any one of these 3 possible conclusions. Yeah? Okay. So as you're finishing up A/B testing throughout the rest of this week and into the weekend, write up your report as follows. 4 pages, 1 page for each of 4 sections. Points will be deducted for poor writing quality. If I can't understand it, I can't grade it. Some of you are graduating this semester and going on and looking for jobs. If you can't communicate verbally or in written form well, they'll go to the next applicant. So here's a bit of a gentle prod to remember to try and communicate clearly. Okay, first section. What were your goals? Some of you chose an already available project, so maybe there wasn't that much to talk about, but please do talk about your project. And how did you go about creating your A/B variant? What ideas did you have? Which ideas did you discard? What A, B, or C or D did you try and it didn't work out, and you went on to E, F, G, and H? That's fine. Focus on the question. What was the question you were trying to answer? Okay, second section is the how. How did you go about doing it? We want to see a description of how you went about implementing this. Please do not copy and paste code snippets. That's not really informative. That's not what we're looking for. You had a vision for your goal. How did you go about translating that into a robot, physics engine, fitness function, evolutionary algorithm, neural network controller? Give us the strategy. Okay. How did you then go about coding up or implementing A and B? Try and avoid just copying and pasting code. Okay. Okay, third section, arguably the most important one. We now know what you did from page 1, how you went about doing it in page 2. Page 3 is what did you get as a result? Provide some results from the AP test. We're looking for 2 things. First of all, did evolution actually occur? So if you include in this section, and by all means you should include in this section figures, if you include fitness curves where we have evolutionary time measured in generations on the horizontal axis and fitness on the vertical axis, assuming in your case higher fitness is better, and we see a fitness curve that looks something like this. The fitness of the best or average individuals in generation 0 doesn't look to me very different from the fitness of the best or the average of the individuals at generation G. Doesn't look to me like evolution occurred. Alternatively, you could run a single run of the evolutionary algorithm, and we could see possibly some increase in fitness from the initial random population in generation 0. Maybe it looks something like this. Did evolution occur? Maybe, maybe not. The answer, as always, is more data. This is maybe A1, this is A2, another run of A, here's a run of B, first run of B, and so on. This average, even just eyeballing it, looks like it's higher than this average. That's what we're looking for. Looks like your evolutionary algorithm, whatever it is, actually did something. Okay. So show us that an evolved robot did better than a randomly generated robot. Okay. Then we're looking to see, then show that one variant did better than another, or that both produced about the same quality of robot. So again, you might want to show us the fitness averages at the end among all your runs of A and all your runs of B, and hopefully there's a clear difference. Even if there isn't, there should be enough curves for us to see that there clearly isn't any difference. Okay. I mentioned already, fitness curves are probably a good idea here. There's lots of other ways you can visualize for yourself and for us whether or not evolution occurred, and whether it did, what kind of evolved solutions did you get? You can include screenshots from the physics engine itself, but that doesn't communicate very much. So we've seen throughout this course many different kinds of visualizations that show what evolution is doing and what it produces. In the lecture on legged locomotion, we saw footprint graphs that show visually the cleanliness of a legged gait. How clearly is there a repeating pattern in footfalls among an evolved locomotion? We saw in the lecture on the Golem project back in the Sim to Real section, phylogenetic trees, so you can plot genetic relationships between individuals in the population. Visualizations of how robust your evolved robots are to new environments. If you remember back to the minimal cognition experiments, they would evolve robots and then play those evolved robots back in many, many different, slightly different environments to those they experienced during evolution. And they plotted generally how well or how poorly those evolved robots did in new environments. This is all optional, but the more visual data, the more visualizations you can provide to us, the more confident we're going to be, and hopefully you are as well, that evolution did something and A is better than B, B is better than A, or there's clearly no difference between them. Okay. Right. Grades will be detected whether if it's unclear which of these three cases happened. Okay. Fourth and final section, you should demonstrate that you thought carefully about your deliverables and the A/B test. By next Monday, you will have done a lot of work. I want you to think back over that process. What was surprisingly difficult? What was surprisingly easy? You all now have a lot of experience wrestling with physics engines and evolutionary algorithms and neural controllers. Each one of these things is non-trivial to get right. Putting them together and getting them to work well together, also non-trivial. What was easy? What was hard? If you had another year to work on this project, what would you have done? How would you have expanded or enriched this project? So what we're looking for in this fourth and final section of your written report is that you didn't just execute You were thinking along the process and starting to think about the implications of what you're doing. Obviously, you have relatively little time to devote to this course and to your final project. Hopefully it gave you a sense of what's possible. We want you to think a little bit about that. What new features would you want PyroSim or PyBullet to have? PyroSim is somewhat limited. We sort of intentionally hid a lot of the nitty-gritty details of the underlying physics engine from you. How might you want to expose or get at some other aspects of the physics engine to evolve more complex robots to do more interesting things? If you were to expand your project in whatever way you're thinking about, given your experiences now with all of these things, what do you think would be relatively easy and what difficult? Okay, that's the written report. Any questions about any of that? No? Straightforward? Okay, let's talk about the oral presentation. Like the written report, it's worth 7% of your final grade. You're going to be submitting by Monday night to Brightspace. You're going to be submitting a link that points to a public YouTube video. After Tuesday, after all the oral presentations, you can take your YouTube video offline if you want, but I need to be able to see your YouTube video. As I mentioned, in the 3-hour block that we have Tuesday morning, we're going to watch 59 oral presentations, so each of you does not have a lot of time. Specifically, you have 2 minutes and 30 seconds. Anywhere between 220 and 240 is okay. If your video is shorter than or longer than that, we've got to get all 59 of them in within 3 hours. Yeah. So you're submitting the YouTube link Monday night, and you're going to be talking over that video Tuesday morning. Okay. So what is going to be in this 2.5-minute video? Like the report, it's going to contain 4 separate sections. And part of your grade for the oral presentation will be clarity of communication. Just keep that in mind. Okay, so you're going to have a short part of your oral presentation summarizing for us somehow what your project was, what you tackled, a little bit of implementation details, what exactly is A, what exactly is B. But I would dedicate the bulk of your 2 minutes and 30 seconds to your results. As we just talked about with static visualizations, it's kind of hard to show us what, if anything, evolution has done to your robot. Now you've got the opportunity in your video to actually show us. So a picture's worth 1,000 words, and a video running at 60 frames per second for a few seconds is literally 1,000 images. You can communicate a lot with a short video. Okay, so what will you likely want to include in this part of the oral presentation? You'll likely want to show the video of an evolved behavior and a random behavior. Probably you want to put them side by side so we can play the spot the difference game. Hopefully you're at this point now in your final project where 5 or 10 seconds worth of a random controller running on your robot in your task environment and a 5 to 10 second video of an evolved controller running on your evolved robot in the same task environment, you'll clearly see a difference. So you should be able within 10, maybe 15 seconds to convince all of us that your evolutionary algorithm actually did something with your robot. Okay. You'll then want to probably do exactly the same thing. Show us the best robot from A. How well did your evolutionary algorithm ever do with evolving behaviors for your robot under condition A? And then show us your best B. How well did your evolutionary algorithm ever do with the best robot evolved under conditions B? And if you're trying to support the claim that B facilitated evolution, we should clearly see that the best B robot is doing a much better job at whatever it is you want your robot to do than your best A robot. Make sense? Okay. Obviously, if you show us one A robot and one B robot, that's anecdotal evidence. That's good. It's a start. We get a sense for what's going on. You'll probably then want to include in your oral presentation the visualizations that you included in your written report. These can be static visualizations, just copy and paste it into your oral presentation. Fitness curves, footprint graphs, phylogenetic trees, whatever you want. That's now not anecdotal data, like here's my best A and here's my best B. It's quantitative data. Here's numbers. On average, it looks like B is doing better than A or A is doing better than B. Okay. When you put together this 2.5-minute video, please make sure that it has no sound, because as I mentioned Tuesday morning, you're going to come up to the front, and for 2.5 minutes, you're going to talk over your video, tell us what we're looking at, explain the axes of your videos, which one is random, which one is evolved, and so forth. Okay, so you're going to be cobbling together bits and pieces of different things. Hopefully, most of you have some screen capture video creation software running now. You might have used it for some of your submissions. If you don't, I recommend the Open Broadcasting System, or OBS. There's a version for every platform. It doesn't cost anything. It's not super fancy, but it'll allow you to cobble together short videos, slides, static images, which is what you're going to need for your oral presentation video. Okay. No points will be deducted for poor video. Not everyone has professional video editing software. That's not what we're looking for. Just make sure that the video quality is good enough that we can see whatever it is you want us to see. Yeah? Okay. Please upload your video to YouTube. I mentioned this already. Make sure it's public, not for kids. Make sure that we can access your URL. Copy and paste that YouTube URL. It doesn't need to be any other text in the Brightspace submission, just that URL into your Brightspace submission by 11:59 p.m. on Monday night. Any questions about any of that so far? Okay. The submission deadline is a hard deadline. If you submit at 1 a.m., 2 a.m., it will not be considered for the following reason. Anna, our long-suffering teaching assistant, is going to be up late on Monday night. She is going to take all 59 URLs and stitch them together in the wee hours of the morning into a YouTube playlist. And that playlist is going to contain 59 submissions. Tuesday morning, starting at 7:30 a.m., you will all be here. There'll be coffee and donuts. I will press play on the YouTube playlist, and that playlist will run with a couple of bathroom breaks built in for 2 hours and 45 minutes. Yeah. I will write on the board Tuesday morning. I will write out the schedule, when you are scheduled to present. Okay. So, as I just mentioned, the TA is going to stitch, this is from last year, there was 60, 59 student videos together in a single YouTube playlist starting, sorry, this is not updated properly. There we go. Okay. I just said all this. Even if you're a few minutes late, you will receive 0 for the oral presentation, because when the TA goes to find your link at 12:53 a.m. and it's not there, she's going to go on to the next student in the list and include theirs in the playlist. So please, please, please get it in on time. Okay. There we go. Okay. At that time, the instructor, will start playing the playlist, including all student-submitted videos. I will make the oral presentation schedule available on the course schedule. I'll put a link down here to the list of when you're presenting. I'll also write it up here on the board for Tuesday morning. Okay. When the student before you begins speaking. So the student who's presenting is going to present on this side of the screen. I will be over here. When you see on the board that your name is next, you're going to go up and stand on deck. And when this student finishes speaking, they're going to sit down. You're going to come to this side. Your video will immediately start playing. You will narrate for us for 2 minutes and 30 seconds, and you will sit down. This is clearly very carefully choreographed because we have a lot of you. There's a lot of amazing content. We want to make sure we can get through all of it in 2 hours and 45 minutes and also give us all a chance to have 2 short breaks in between. Fair? Make sense? Okay. So when the student, before you begin speaking, over on the far side of the screen, when your video starts, come to this side of the screen, narrate over your video, and reseat yourself. Okay. This means that when your video starts, you should start speaking immediately. If you run long, you need to practice. You got to get your timing right. If you run long, I don't have a long hook, but if I did, I'd use it. The next video will immediately come up. You will be ushered back to your seat, and the next student will start speaking. So be sure to practice. The good news here is your presentation is only 2 minutes and 30 seconds long. So upload your YouTube video, put it on loop, and narrate 10 times, 20 times, 30 times in over an hour or 2 hours. And at that point, you'll have it memorized. The pacing will be fine. Sound fair? Okay. Years and years ago, I had to give a talk at MIT. The talk was 90 seconds long, and they did the same thing. If you ran long, they turned off the mic and they turned off the lights in the auditorium. Very harsh. Drove down from here to Boston, took my wife with me. I practiced in the car in the 3.5-hour drive to Boston, this 90-second spiel over and over again. If you ask my wife today, she could probably recite it from scratch, unfortunately for her, but there you go. Okay, practice, practice, practice. Make sure you get the timing exactly right. Okay, questions. You're going to see a lot of amazing content. You're probably going to have questions of your fellow students. How did you manage to pull that off in the physics engine? Why did you get that evolutionary result? Why do you think the recurrent connections in the brain of your robot helped with that? Please do ask your fellow students questions. We don't have time to do it in real time, in situ, while they're presenting. So during the 2 10-minute breaks, find your fellow students, ask them questions. Okay. Collegiality. Okay. 2 hours and 45 minutes, even with 2 10-minute breaks, is a long time to sit and pay attention. You've all done a lot of hard work, so do each other the courtesy of paying attention. There will be a temptation to tune out, to check your device, and so on. We all know how this goes. You're all going to be sleep deprived next week. I know the reality of this situation. Please do pay attention. You're going to see a lot of amazing material. Okay. This includes staying until the end of everyone's presentations. Please do. Okay, that's the written report and oral presentations. Any questions about any of that? All good? Okay. Looking forward to seeing what you've come up with. Okay, back to lecture. We are nearing the end. So we are going to finish over the next few minutes lecture 22, when we were talking about evolving bodies and brains of soft robots, and there will be a relatively short lecture on differentiable robotics to follow. Just as a reminder, in this last section, we're looking at what now are the 4 main branches of robotics: traditional rigid robots with rigid links and rotational joints, soft robots made out of rubber and silicone and liquid foam metals, exotic materials, differentiable robotics. These are robots that are created in a differentiable physics engine, and as we'll see in a moment, this allows us to remove the error from the trial and error part of an evolutionary algorithm. It allows us to design bodies and brains for robots much, much, much faster than you're doing now with an evolutionary algorithm. We'll then talk about the 4th and final and relatively recent branch of robotics, now known as biological robots or biobots, and xenobots, which you've already seen, are sort of the most famous example of that so far. Okay, back to soft robotics. So we were looking at, we ended last time by looking at Voxcraft here. This is a soft robot simulator. It simulates soft robots by assuming the robots are made up of a whole bunch of 3D pixels or voxels. Those cubes or voxels are attached to their neighbors by rigid beams, and each one of those rigid beams that attaches two voxels together, each beam has 6 numbers associated with it, and I realized that I misspoke last time when I described those 6 numbers. 3 of those numbers describe linear stiffness, meaning that if the x positions of the 2 ends of a beam move relative to one another, the bigger that first number is, the more it resists this kind of motion. The second number describes how much the beam resists this kind of motion. The third number represents how much it resists this kind of motion. Imagine the 2 ends of the beam, the positions of those 2 ends are trying to move apart along the x-axis, the y-axis, or the z-axis. The bigger those 3 numbers are, the stronger the beam is, and the more it resists those 3 kinds of shearing. The 4th, 5th, and 6th number describe how much the beam resists 3 different kinds of rotating. This, bending, this one, and this one. Yeah? So every pair of cubes that you see here, there's a little beam hidden inside, and some of these are rubber beams. They allow the 2 ends to move relative to one another quite a bit. Some of these beams are more like steel beams, and they're resisting shearing and rotation quite a bit. Okay, so I described all of that last time. That's the simulation. My group, together with another group at Yale, has taken some of these evolved designs and built them in reality. And I forgot to bring in this robot. It's in my office. You'll notice that we've taken every simulated voxel and built a physical voxel. Might be a little bit difficult to see from this picture. Each one of these cubes or voxels is empty. There's just regular air inside. You can see some hoses attached. So these are like little tiny bicycle tires. We can pump air into a voxel or pull air out of the voxel. Here we're putting a little bit of air into the pink ones, but not the yellow one behind it. And here we're compressing or pulling some of the air out. This is meant to the expansion is meant to represent what happens in simulation. When you take one of the beams, cut it in half, turn it into a piston, attach a motor to that piston, and that motor extends the length of that piston, pushing those voxels apart. If you imagine cutting a whole bunch of the beams and turning them into pistons and telling all of those pistons to get longer, all of the voxels pull apart from one another in simulation, and you get more or less the same sort of thing in reality. If the motors attached to all the pistons tell the pistons to shrink in length, all of the voxels scrunch up close to one another, and you get something in simulation that looks kind of like this. As you can imagine, crossing the sim to real gap with these kinds of soft robots, not trivial. Here's a simulated 4-legged robot up here. This was us just trying to build this technology in reality and testing out what happens if we flow air into all of these voxels. You get not a walking 4-legged robot, but a breathing 4-legged robot. We've been working on this for a couple of years, not trivial. We haven't quite got this robot to walk yet, but hopefully one of these days. Okay. I'm going to speed up this video. And what you're going to watch is actually a former student who took this course, Sam Kriegman, who's actually going to go about building one of these soft robots in reality. He's going to start using this yellow vial here, which contains dragon skin. Dragon skin, as you can see, is a powdered plastic. And when you dope it with a few materials, it's actually liquefied. It's a liquefied silicone or rubber. And we're going to mix all of these ingredients together in something that's spinning them around quite a bit. It's been heated up a little bit, so it's liquefied, basically liquid silicone or liquid rubber. We're going to pour it into this mold, spread it out a little bit, and at room temperature, it will gradually set and become the 5 sides of these hollow voxels. We're going to put it on this fancy spinny thing and spin it a little bit to evenly coat the sides. This is like a waffle maker for soft robots. Then we're going to bake it off for a little bit, heat up the temperature a little bit to set the silicone, even out things a little bit. Oops, sorry. Even things out a little bit. Okay. You can see Sam has pulled out some of these voxels now. He's got 4 voxels in the back there with 5 of the 6 sides. He's going to add the 6th and final side to these voxels by putting before he does, he's punching holes between neighboring voxels. When we apply the hose to one side of the robot and we supply pressurized air through that hose into the robot, that pressurized air is going to enter the voxel. But if there are holes on any side, we can send that air through different channels within the body of the robot. And we can select which voxels are going to increase and decrease in volume when we supply air in and out. Sam's cutting away the excess material. He's going to add the hose now to one side, seal it up. He's created now 2 of these so that we've got our little simple 3D robot. He's going to add a little syringe, and he's going to apply some pressurized air. And again, we don't quite get a robot that walks, but at least we get a robot that deforms. All of this material costs less than $200. If you'd like to try it at home, be my guest. Okay, so not sim to real, but real. Okay, all right, let's jump back to sim for a moment. This particular physics engine, this soft robot physics engine VoxCAD that we were just talking about, it was originally released back in 2014 as an academic paper. And what you're seeing now is an evolutionary algorithm that's been wrapped around VoxCAD. And the evolutionary algorithm is dictating where to place voxels to create the 3D geometry of the body of the robot. Remember, we're interested in evolving the robot bodies. And you'll notice here when one relatively low fit robot and a more fit robot. So like we were just talking about for your oral presentation, here's some anecdotal evidence that an evolutionary algorithm can find the right 3D geometry for a soft robot in simulation that causes it to move from left to right. You'll notice that some of these voxels have different colors. These colors indicate properties of the underlying beams, the stiffness of the beams that connect those voxels to other voxels. So I'll come back to those material properties in a moment. How did Professor Cheney and his colleagues evolve soft robots? What did the evolutionary algorithm look like? He used HyperNeat. If you remember HyperNeat, we talked about this a while back. HyperNeat is a particular kind of evolutionary algorithm that evolves populations of neural networks. Each one of those neural networks is a compositional pattern producing network. Just as a reminder, I've put an example CPPN over here. A CPPN is a network that paints patterns in 2 or 3-dimensional space. It paints colors, it paints synaptic weights. It's up to you on what it paints. In this case, this CPPN is going to visit a bunch of points within this empty cube and decide that CPPN is going to either paint or deposit a voxel at that location, or it isn't going to. Okay, I just mentioned that the CPPN is going to paint or drop voxels within an empty 3-dimensional volume. So we need at least 3 input neurons for our CPPN, X, Y, and Z. So when we start the CPPN, we go to position 0, 0, 0. We feed 0, 0 in, and we look at one of the 2 output neurons in the CPPN. In this particular experiment, the CPPN had 4 input neurons. We'll talk about D in a moment, and 2 output neurons. The first output neuron, when we feed in 0, 0, 0, we look to see whatever value arrives there. We push that raw neuron value through an activation function that turns it into a binary value. So basically, threshold it. If that raw value is negative, set that neuron to 0. If the raw sum arriving at that neuron is a positive value, set that neuron to 1. So this particular output neuron is going to dictate whether or not to drop a voxel at that location. So far, so good? Okay, so imagine we take this CPPN, visit a bunch of points distributed in a regular lattice inside this cube, and it's going to either drop or not drop voxels at each of those locations. That's going to produce, for example, some 3D geometry. In this example, this CPPN happens to drop voxels at these locations and not drop voxels at these other locations. Let's talk about the second output neuron in these CPPNs. This second output neuron is going to dictate the material property of the voxel. And the different colors here represent the different material properties. I'm going to play the video of these evolving robots in a moment. In this video, you're going to see a total of 4 different colors: green, red, light blue, and dark blue. As I mentioned, these colors are going to represent how stiff or how soft that voxel is, how stiff or how soft that beam is emanating from that voxel. So let's take an example. The light blue voxels, as you're going to see in the video, these are passive soft voxels. They're meant to be the robot equivalent of fat. Some of us have more or less of it. It's passive soft material. Fat can be pushed or pulled by more active materials like muscle. So let's take this light blue voxel here. This light blue voxel, although you can't see it, it sends a beam from itself to this voxel, to that voxel, to that voxel below it. So this particular voxel has 1, 2, 3 neighbors, which means there's 1, 2, 3 beams emanating from this light blue voxel. This light blue voxel is a passive soft voxel, so those 3 beams are like rubber beams. They're very soft. They can be pulled and pushed by the forces acting on the neighboring voxels. So far, so good? Okay. This second output neuron, which is painting colors onto these voxels, in this particular experiment, they took that raw sum, which is a floating point number. They pushed it through an activation function that discretizes that float to 4 possible integers: 0, 1, 2, or 3. Those 4 integers correspond to the 4 different colors you're going to see in the video in a moment. Okay. Let's talk about the fourth and final input neuron. D, remember we're going to visit a bunch of points distributed in a regular lattice inside this 3D cage. D is the distance of that point from the center of the cage. Why did the investigators include D? Remember back to when we talked about HyperNeat. HyperNeat was designed so that even if you create a random CPPN, you cobble together a bunch of neurons and synaptic weights and different activation functions, which are the things that are sitting inside the neurons here. You cobble together a random CPPN, and it will tend to produce or paint a non-random pattern, things with regularity in them. You'll notice that there's one big sort of 3D clump here within the cage. It's not a random sprinkle of different colored voxels inside. There's already a little bit of regular patterning here. Why include D? The distance from the center of the cage. Let's imagine a very, very simple CPPN. Let's assume that only the D neuron connects to one of the two output neurons, which is the presence neuron. So the greater D, the greater the chance that there will be a voxel dropped at that location. What 3D shape would you get? Let's keep this really simple. We'll assign a weight of 1 to this synapse. As we travel around all the points within this empty cage, we feed in the XYZ position of those points, but it doesn't affect this neuron, so we can effectively ignore them. At each one of these points, we compute its Euclidean distance from the center of the cage, and that's the value that goes in here. That value is multiplied by the synaptic weight of 1. Let's assume we have an activation function inside here that's going to spit out either a 0 or a 1. This CPPN, the greater this value is, the more likely there's going to be a voxel placed at that position inside the empty cage. What are you going to get? What 3D shape is it going to produce?
It'd be like a cube that was hollow in the center.
It's a cube that's hollow in the center. Think about the 8 corners, right? If we visit the 8 corners of this cage, D is going to be maximum, and the probability of dropping a voxel is maximized. So this simple CPPN is going to paint a whole bunch of voxels at the corners and at the 6 faces of this empty cage and sort of fill it in. And as you mentioned, as we get closer and closer to the center, including the very center of the cage, D will now be 0. 0 times 0 is 0. We're definitely not going to place a voxel at that location. What is the shape of this hollow aperture inside this now non-empty cage? It's a sphere. They added this 4th input neuron to kind of bias HyperNeat, that's going to search over the space of CPPNs to produce things that are kind of spherical, kind of blobby, like this thing. Yeah. So we've seen this many times in this course. The human investigators are kind of putting a little bit of intuition into the evolutionary algorithm. They're biasing it to produce blobby type things rather than very asymmetric, weirdly shaped things. Okay, bit of a minor detail. Okay, that's a lot of build-up. Let's see the video of how this all works. Okay, as I mentioned, we're going to see in the preamble here an explanation of these 4 different material properties. I'm just going to pause things here for a moment. Here's the 4 different material properties that the voxel can have. We already talked about the light blue one. This particular voxel, if it has any neighbors, it sends out rubberized beams to connect to them. Let's talk about the dark blue one. This one is meant to be the soft robot equivalent of bone. I mentioned this before. When we talk about soft robots, we don't literally mean that they're entirely soft. It means that soft robots could be a mixture of soft and rigid components. Here's the rigid components. If a CPPN paints blue onto any voxel, and that dark blue voxel sends out beams to its neighbors. Those beams are steel beams. They're rigid and stiff. So if there are any neighbors of a dark blue voxel and those neighbors pull or push on the dark blue voxel, that dark blue voxel will obey the pulling and pushing. Yeah? We are all collections of fat and bone that work together in particular ways. The red and green voxels, these are active voxels. These are muscle. Let me unpause for a moment. You'll notice that they're increasing and decreasing in size, and you'll notice that they're increasing and decreasing in size in antiphase to one another. What this means is that for these voxels, if the CPPN paints red onto any one voxel, and that red voxel has neighbors, that red voxel cuts all of its connecting beams in half, turns them into pistons, and that red voxel sends out sinusoidal patterns to all of its beams that pull and push, extend and contract those pistons. That's visualized in the videos you're going to see in a moment by the voxel itself getting bigger and smaller. Everyone picture this in your mind. You've got a red voxel that is literally pulling and pushing on its neighbors using a sinusoidal pattern. So those neighbors are being pulled in and scrunching the red voxel, and then the pistons emanating from the red voxel are pushing on the neighbors. Those neighboring voxels move away from the red voxel, and we're going to, when we visualize or draw this red voxel, we're just going to draw it getting bigger. Yeah? This is not unlike how the muscle groups in your body work. The tiniest little muscle fibers in your body, they expand and contract and get a little bigger and smaller in volume, and they end up pulling and pushing on other things. Muscle itself can't cause you to move. Muscle has to pull on something else, like, for example, bone. Okay, the green voxels are exactly the same as the red voxels, but the green voxels at any time step in the simulation, whenever the red voxels are pushing on their neighbors, the green voxels are pulling on their neighbors. If there's 2 or more red voxels in the body of the robot, all of those red voxels push out on their neighbors at the same time, and they all pull on their neighbors at the same time. You're going to see this in the video in a moment. All the green voxels, they pull on their neighbors at the same time and push on their neighbors at the same time. So we have 2 different types of muscle, muscle 1 and muscle 2, that are in antiphase to one another. This is a bit of a biophysical detail that we've actually mentioned in this course before. In you, when you're walking or writing or doing anything, some of your muscle groups are pulling and pushing, but they're not doing it randomly. Usually, there are muscle groups that are pulling at the same time that there are other muscle groups that are relaxing. And then it alternates. What is this called in us? Anybody remember?
Antagonistic muscles.
Agonist and antagonistic muscle groups, right? When I flex my bicep, I relax my tricep, which causes this to happen. If I want this to happen, I compress my tricep and relax my bicep. Yeah? Same idea here. Let's see what evolution makes of these 4 materials. Okay. You're going to see a series of videos superimposed on top of a fitness curve. Actually, I guess we'll see some videos first. Okay, so here's one with some red muscle groups. You'll see the light blue fat and the the dark blue bone. Here's red and green working in opposition, and you can see why this is helpful. When this paper was published, the reporters that covered the work referred to it as Jello robots for obvious reasons. Again, you can see the nature of CPPNs at work here. These are not random collections of voxels. There's already a bit of regularity in these body plans. Okay, here we go. Here's a random robot, a robot produced by a random CPPN. Here's the most fit robot at the second generation, most fit robot at the third generation, and then we're going to start to skip ahead in evolutionary time. Here's the most fit robot at generation 50, 100. I'm going to pause for a moment. What's already happening 100 generations into this evolutionary algorithm? What's changed since the first random robot in the first generation? This is a random robot.
Leaving the box.
Sorry? It's leaving the box. So evolution is working in this case. Fitness is going up over evolutionary time, and the robots are evolving to move further to the right, our favorite fitness function. What else is happening?
There's a lot more muscle and less of the soft tissue that it starts with.
Absolutely. So this is kind of perverse instantiation. Maybe this is kind of a gray zone. We asked evolution to evolve the bodies of these robots to travel as far to the right as possible. And basically, it's made a big ball of agonist and antagonistic muscle groups. Not quite. There's a little bit of fat remaining and a tiny little bit of bone, but apparently the evolutionary algorithm doesn't need much of it. And in some cases, there's very little of anything other than these two opposing muscle groups. I don't think we'd be able to build a physical version of any of these robots anytime soon. As usual, the evolutionary algorithm is being overly optimistic on what it thinks these robots in reality are capable of. Okay, in the interest of time, I'm going to skip over all of the fun results that they got. You can watch the rest of this video at your leisure. Okay, we're running short on time, so I think I'm going to end our lecture on evolving bodies and brains of soft robots here. Consider the rest of this lecture optional. Any questions about evolving soft robots before we move on to differentiable robots? Going once, going twice. Okay, all right. So lecture 23. This is a shorter lecture. Congratulations, you've now reached the bleeding edge of human knowledge as it relates to automatic optimization of robots. Some of you have been taking classes since kindergarten, and you've been learning things that have been known for hundreds or thousands of years and have been learned by many, many, many people before you. In this lecture, we're now going to talk about differentiable physics engines and differentiable robots that have been around for about 3 years. And it's probably about 30 or 40 or maybe 50 people on the planet that are very comfortable with this material. So if I lose you in lecture 23, not to worry. We're at the bleeding edge here. Try to follow along as best you can. Okay, here we go. Let's start our discussion of differentiable robots with a hopefully familiar friend at this point. Let's take a Bratenberg vehicle 2A, which loves the light. Let's assume that we've built this particular Bratenberg vehicle inside a differentiable physics engine. We've built it in the normal way. We've built a rigid body. We've attached 2 light sensors to the front of this body. We've built simulated wheels on the back of the robot, and we've connected the left light sensor to the right wheel and the right light sensor to the left wheel. And we want, in this case, let's assume that we want to find just 2 numbers. We want to find the value of the 2 synaptic weights that will cause this robot to turn towards the light. Hopefully this is familiar, and it's so familiar and relatively easy that this is one of the few cases where we can actually optimize this robot in our head. We can come up with these two synaptic weights. What are they? Turns out there's lots of them that work. There's also lots of them that don't work.
Can you just make them both as high as possible?
Yep, let's make them both positive numbers. Same pair of positive numbers, different numbers.
Well, negative. I'm not sure.
Okay, it's all right. When in doubt, go with the identity function. 1, 1. What happens if we label both of these synapses with a weight of 1? In this particular condition in which the light source is in front of and to the left of the robot, what would a Bratenberg vehicle armed with 1, 1 do at this point in time? Robots sense, think, and then act. So what does the robot sense at this point in time? What's happening with the light sensors?
They're getting different values of intensity.
They're getting different light intensity values. How? What's the difference?
Well, the left sensor is closer to the light, so it's going to have a higher, the calculated value after the synaptic weight is going to be higher than
The value calculated after the synaptic weight is going to be higher. The light values themselves, this light sensor value is going to be greater than this light sensor value. So this bigger number times one is going to cause this wheel to spin faster than this smaller number multiplied by 1 will cause this wheel to turn. The right wheel is spinning faster than the left wheel. It turns towards the left. So 1, 1 produces the behavior that we want. -1 won't work. It'll cause this wheel to spin backwards faster than this wheel spins backwards, and it'll turn back and away from the light. So I want you to imagine all possible pairs of real values, some of which produce better photophilia, love of the light, turning towards the light, and some of these pairs of values will produce photophobia or turning away from the light or something else. So let's go back to a separate, hopefully familiar friend, which is a fitness landscape. For today's purposes, I want you to assume that we're looking at a two-dimensional, a fitness landscape in three-dimensional space. The surface of this landscape is going to be in 2 dimensions. It's going to be theta L and theta R, where theta is going to be the weight of the left sensor, left synapse. We'll call this the left synapse. This weight is theta L. This weight is theta R. If we're looking down from above onto this surface, any one point on this surface corresponds to a particular pair of values of theta L and theta R. We can take that particular pair of values, drop it into our Bratenberg vehicle, and measure its fitness. How well or how poorly does it do at turning towards the light? So far, so good? Okay. If we were lazy and we didn't want to try and come up with this pair of values on our own, we might use an evolutionary algorithm. We might start by creating a population of random pairs of synaptic weights. Each one of these points represents a genome. We take that genome or those pair of weights, drop it into the vehicle, measure fitness, and we have the height of the point. Let's assume a higher value is better. It represents more fitness, more photophilia. So imagine these points sticking out of the board. The further out of the board they are, the better that pair of values is. The closer to the board they are, the less photophilia they produce in the Bratenberg vehicle. So far, so good? Okay, so in an evolutionary algorithm, if we evaluated all of these 1, 2, 3, 4, 5, 6, 7 points, we would know their heights. Where do we go from here? What do we know about the neighborhood around each of these points? Let's imagine this particular point is really good. It's got very high fitness. It's sticking out of the board. This one, terrible. What do we know about the neighborhood?
You know about the like relative fitness, like magnitude of like each point.
We know the relative fitness. We know this one is much more fit than this one. That's true.
The points around each of them are probably similar.
The points around them are probably similar. Probably true for the Bratenberg vehicle, which is very simple. Small changes to a pair of values here is going to produce a small change in behavior. So you're right. We can probably guess that a new point, question mark, nearby a highly fit individual is probably going to be also pretty fit, if not even more fit. That's true in very simple situations, but it may be more complicated than that. It may be that this point is highly fit, and this point, very, very close, is also pretty fit, but another point just a little bit away is really bad, and then this point yet even further away is good again. In theory, we can't even trust that neighbors are good, because what do we mean by neighbor? How close? How bad? Remember when we talked about fitness landscapes at the beginning, we used this metaphor of going for a hike with your friends on Mount Mansfield, but you're hiking in fog and there's no Wi-Fi. There's no satellite. So you don't necessarily know which way to go. It might be actually that for this individual who's highly fit, if you go in this direction, meaning you find new pairs of values in which theta r is higher, but theta L stays about the same relative to the parent, things actually get better. If you go in this direction, you're still dealing with neighbors, but maybe things get worse. You don't actually know in what direction to go. Yeah? So there's a problem with evolutionary algorithms. You kind of have to guess. You have to sort of make something up and hope for the best. Wouldn't it be great if the fog parted a little bit and you could actually see maybe a few steps ahead of you that there's a bit of a rocky slope leading up in front and to the right of you? Wouldn't it be great if you could see a slope or see a gradient that would tell you which direction to travel to get to a point of even higher fitness? What we're going to introduce in a moment is we're going to replace the evolutionary algorithm with gradient descent. So the first change we're going to make is we're no longer going to talk about fitness. We're going to talk about loss. This is a fancy term from machine learning, which just means that when we're moving around in the space trying to find good pairs of values, we're going to try and minimize loss. We want loss to be as low as possible. So you go hiking with your friends in Death Valley. If you do this in reality, take a lot of water with you. You're trying to get to the lowest point. Now you're surrounded in smog, let's say. We're dealing with the Southwest, right? Or forest fires. You also can't see. You're trying to get as low as possible. You hope the smog or forest fire smoke will clear a little bit so you can see a little bit how to go down. So far, so good? Okay, so in gradient descent, this is an optimization method that's actually going to give us this direction. It's going to allow us not to start to make random guesses from here. We don't need to make randomly modified copies of this pair of values. We are going to know, thanks to the gradient, that if we make theta r a little bit larger, and if we make theta L a little bit smaller, we know, it's guaranteed, that if we take a new pair of values along this direction and drop it into the vehicle, we know it's going to do a better job at whatever we want it to do. That's the intuition behind gradient descent. There's no more randomness. We now are no longer doing trial and error. Everybody get the intuition? Okay, let's go. All right. At the moment, we've been talking about a couple of parameters. Both of them are neural parameters, the synaptic weights. For fun, I'm going to introduce a couple of other parameters that we're going to try and do the same trick with. I'm going to pick the horizontal position of the left light sensor. Okay, let's imagine in this particular vehicle that we have synaptic weights 1 and 1. Let's assume that we change x. We move the left light sensor a little bit further to the left. How has that changed the behavior of the robot? If this second robot still has the synaptic weights 1 and 1, does this particular robot do a better job at photophilia than this robot? I see you nodding your head. How do you know?
Because it's closer to the light source.
It's closer to the light source. This sensor is closer to the light source, which means at this moment in time, what's different?
The sensor value is higher.
The sensor value is higher. Multiplied by 1 means this wheel turns faster. So this robot at this moment is better than this robot at this moment. That we can be certain of. How about in general? I start chasing this robot, and alternatively, you with the flashlight chase this robot. In general, which one does better?
The one that's more balanced.
The one that's more balanced?
Yeah,
How come?
that one.
Yep.
Well, because the light is not necessarily always on the left, so you don't always want to bias towards the right wheel.
You don't always want to bias towards the right wheel. You'll notice also that in this robot, the horizontal difference between the two light sensors is greater than in this one. What does that mean? It's actually helpful for this kind of vehicle to have the two light sources, the two light sensors horizontally separated. Why?
It's more sensitive to like light on either side.
It's more sensitive to light on either side, and
Especially light on the left side.
what happens in that case?
It'll like turn quicker.
It'll turn quicker. Other ideas?
Well, it just has a wider range of, like, distance that it can see the light from.
It's a great, yeah, absolutely. Maybe it can just see further. The difference between these two light sensor values is also greater, right? If you have these two light sensors right up next to one another or sitting right on top of one another, the robot can't tell left from right. So we could think about trying to optimize or find a good value for x as well. Now we've moved into four-dimensional space, unfortunately. So now we've got a three-dimensional landscape inside of a four-dimensional space. Hard to think about. So let's not do that. Let's do the following. Let's remove one of these weights and put x here and leave this one. So we're going to try and optimize. We're going to find a good value for x, and we're going to try and find a good value for theta L, the left synaptic weight. I'm trying to keep things to 2 dimensions so I can draw them for you. Let's just assume that we set this particular synaptic weight to 1. We're going to make our lives easier. So I'm going to drop the L subscript here. So we're going to still try and find pairs of values. We're going to try and find good x's and good thetas that produce good photophilia. So far, so good? Okay. Let's think about PyBullet or any physics engine. So in a physics engine, we have a light source. We compute the distance between the light source and the light at a given time step, and we set the value of this light sensor to the inverse of this distance. The greater this distance, the smaller the value we place here. During a single time step of the physics engine, we take that light sensor value, multiply it by the synaptic weight. That gets sent to the motor, which dictates omega, the rotational velocity of the wheel. As we just said verbally, if this value is high or is higher than this value, this means omega for this wheel will be bigger than omega for this wheel. Omega is the rotational velocity, how fast this wheel is spinning. So when you run a physics engine, any physics engine, it does most of this for you. Yeah. So we take the value of the motor neuron, we send it to the motor, and it gives us back the rotational velocity. And finally, this rotational velocity is used by the physics engine to compute the new position and the new orientation of the robot. That's taken care of for you by the physics engine. What the physics engine can't do for you, at least not yet, it can't tell you what x and theta should be. You just let's say we put some random x and theta into the physics engine, and we ran the physics engine forward one time step. Forward meaning we computed sensation, then thinking, then action, and the action of the robot updates the state of the robot, which changes what it senses at the next time step, which causes what it does at the next time step, and time step to time step to time step to time step, we get the robot's position and orientation changing inside the physics engine. We're going to refer to this from now on as the forward pass. We're passing forward through the physics engine from stuff outside the robot to its sensors, to its brain, to its motors, to its wheels, to new position and orientation. Okay. That's going to produce, at a given time step for us, loss. Usually, we're computing fitness to be higher fitness is better. In a differentiable physics engine, it's a little bit awkward. We need to define behavioral loss, meaning how inefficient is the behavior of the robot. If the robot does a really crappy job of photophilia, it follows the red arrow and actually turns away from the light. If we were to take the Euclidean distance if we took the difference between these two trajectories, this is the one we want. We know this is what we want it to do. This is what this robot with this pair of x and theta values actually did. There's high behavioral loss, high behavioral inefficiency. We want the differentiable physics engine now to tell us what direction we should move in order to reduce behavioral loss. We want to drop down in the loss landscape, Death Valley. So far, so good? Have I lost anyone yet? Okay, so at this point in time, this particular pair of values is suffering high behavioral loss. So here comes the calculus. The physics engine knows that this particular omega, this amount of rotational velocity, caused the robot to turn a little bit in the red direction. So I'm going to draw another picture down here. And I'm going to put on the horizontal axis here omega. And the physics engine knows that omega was just whatever value omega just was. And it knows that loss was whatever it was. We compute loss inside the physics engine. So at this moment in time, the physics engine knows omega. It knows what the rotational velocity is of the wheels at this moment in time. And it just used F equals ma. This is velocity. We can turn velocity into acceleration. It knows the mass of the wheels. So the physics engine computed the forces that caused the robot to move in this direction and get this amount of loss. If we color in all of this material here, that's loss. It's a total number. So the physics engine knows L, it knows omega. And the physics engine has this equation. It knows how it calculated this. So we're not going to do it, but in a differentiable physics engine, the moment it finishes a simulation, it takes these values and it takes the derivative of this with respect, it takes the derivative of L with respect to this. And so at this point, at least, it knows the gradient. A differentiable physics engine knows for this value of omega, it knows that if you were to decrease omega a little bit or increase omega a little bit, it knows how L is going to change. It does all that for you. This is the whole magic of physics engines. It does a lot of the dirty work for you. In this case, a differentiable physics engine's going to do some of the calculus for you. It's going to find the derivative at this point, which gives it the slope. It knows how L will change as omega changes. Everyone with me so far? I'm skating over the actual derivation here. You can go and do this if you like. It's a little bit beyond our purposes for today. Okay, we're out of time for today. We're going to pause here. You have a quiz due tonight. You're working on your A/B testing. We'll see you for the final lecture on Thursday. Thanks very much.